Both the source and the listener are stationary. Take a look at this. You are standing at point A and your friend is standing at point B. In the middle, between the two of you guys at point A and B, there's a car that is playing music. So you standing at point A and the friend standing at point B will experience the music in the very same way. The frequency of sound that is emitted by the car is the very same frequency of sound that is going to be observed or experienced by the two of you guys. That is because the distance between the crests and the troughs is remaining the same. Both the source and the listener are stationary. The frequency is not changing. Let's take a look at this example. You are still standing at point A and your friend is standing at point B. But the car is moving towards B. The car is moving towards the point B. As you can clearly see, there's a compression here on the crests and the troughs. There is a smaller wavelength and as a consequence, a higher frequency. So clearly from this sketch, you can see that if a source is moving towards a stationary observer, your friend at point A, the friend is going to observe a higher frequency compared to the one that is emitted at the source. And you, at the other hand, at point A, if there's a source that is moving away from you, then you're going to experience a lower frequency because the distance between two successive troughs is increasing. We have a longer wavelength and as a consequence, a lower frequency. This change in the frequency observed because of relative motion between a sound source and the listener is what we refer to as the Doppler effect. You can see from this example that it is the sound source that is moving. What about a case where the listener is moving? Let's take a look at that. Here we have the listener that is moving towards a stationary source at point A. When the listener is moving towards the stationary source, the wavelength becomes shorter and the frequency is higher. And lastly, take a look at this case. We have a listener that is moving away from a stationary source. When the listener is moving away from the stationary source, the wavelength becomes longer and the frequency becomes lower. Just like in this case, we are given the frequency emitted by the source. With this frequency emitted by the source, we can be able to find the frequency that is observed by the listener using the Doppler effect. Let's go ahead and take a look at that. This is the equation we use to calculate the frequency heard by the listener. FL is the frequency heard by the listener or the frequency observed. The SI unit is hertz. And then on the other hand, we have Fs. Fs is the frequency of source, the frequency that is emitted by the source. It is also measured in hertz. And then we have V. V is the speed of sound in the medium and it is measured in meters per second. Usually, we're talking about the speed of sound in air, which is about 340 meters per second. It will depend on what the question says. It's not always 340. In other special cases, maybe we're talking about the speed of sound in water, which is way more than 340 meters per second. So V is the speed of sound in the medium, which will depend on the question you have at hand. And then FL, that is the velocity of the observer or the velocity of the listener in meters per second, obviously. And then VS is the speed of the source, still in meters per second. So this is the equation we use to calculate the frequency heard by the listener or observed. Taking a look at this equation, you will realize that we have plus or minus VL plus or minus VS. That plus or minus will depend on the situation you have at hand. Let's go ahead and take a look at that. The first scenario, we have a source that is moving towards a stationary listener, and this is how the equation looks like. Followed by a scenario where the source is moving away from a stationary listener, and we have our equation. On the denominator, we have V plus Vs. And then let's take a look at the third scenario. The listener is moving towards a stationary source. We have V plus VL on the numerator. And lastly, we have a listener that is moving away from a stationary source. And on the numerator, we have V minus VL. So these are the four versions of the equations. But don't worry, you don't necessarily have to memorize all these four. As we are going through the examples, you will have an intuitive understanding of which equation you need to use and when, from just that one main equation that we have. Take a look at this scenario. The first scenario that we talked about. We have a stationary source and stationary listeners. And we are saying that the frequency emitted by the source is going to be the very same frequency that is observed by the listener. Take a look at this example. The siren of a stationary ambulance emits waves at a frequency of 800 Hz. Determine the frequency of sound heard by stationary observer if the speed of sound in the air is 340 meters per second. The frequency emitted by the sound source is 800 Hz. We are interested in the frequency observed by the listener. So we want FL. What are we given? We know that the velocity of the sound source is 0 meters per second. It is stationary. And then the velocity of the listener is also 0 meters per second because the listener is stationary. But we are given the velocity of sound in air, which is equals to 340 meters per second. We know that FL should be equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. We want FL. This is what you're interested in. We are given FS, V, VL, VS, and now it's just a matter of substituting. So FL will be equals to, what is the speed of sound in air? In our example, 340 plus or minus VL. Our listener is stationary, so plus or minus 0 is just 0. So we can forget about that. Divided by V plus or minus VS. Well, the speed of sound in air is 340. Our source is stationary, so plus 0 or minus 0, we can also just forget about that because it doesn't make any difference. Multiplied by Fs. The frequency emitted by the sound source is 800 Hz. So we're going to have 800. Now let's go ahead and take a look. 340 will cancel out with 340. So we have the frequency observed by the listener being equals to 800 Hz. So there we go. We have the frequency that is observed by the listener. And it is the same frequency that is emitted by the sound source. This is because there is no relative motion between the listener and the sound source. So the frequency emitted will be the same frequency that is observed by the listener. Example 2. We have an ambulance that is moving towards a stationary listener with a velocity of 30 meters per second. So in this situation, you can see that our sound source is moving, right, towards a stationary listener. The frequency emitted by the ambulance is 600 Hz. Calculate the frequency that the listener will detect if the speed of sound in air is 340 meters per second. So the sound source is moving towards the listener. We are expecting the frequency observed to be greater than that which is emitted. So let's go ahead and take a look. The velocity of the sound source is 30 meters per second. So let me write that down. And then the frequency emitted is 600 Hz. So Fs, frequency emitted by the source, that is 600 Hz. Calculate the frequency that the listener will detect. So we are interested in FL. If the speed of sound in air is 340 meters per second. So we have V being equals to 340 meters per second. The ambulance is moving towards a stationary listener. So VL is equals to 0. Our listener is stationary. So FL, the frequency observed by the listener, is equals to V plus or minus VL divided by V plus or minus VS. Everything multiplied by Fs, where Fs is the frequency emitted by the source. So V, that is 340, the speed of sound in air, plus or minus VL. Our listener is stationary, so plus or minus 0 we can just forget about that and have 340. Everything divided by v, the speed of sound in air, 340, plus or minus the velocity of the sound source, the ambulance. The ambulance is moving towards the stationary listener with a velocity of 30 meters per second. So we're going to have minus 30. We're supposed to have plus or minus Vs. Because it's moving towards, we have minus. You can see here in our first scenario that if we have a source that is moving towards the stationary listener, we have minus Vs on the denominator. Let's carry on. So we're going to have minus 30 multiplied by the frequency emitted by the source, which happens to be 600 Hertz. So now I just need to put that in my calculator, and we have the frequency that is observed by the listener, and this is equals to 658.06 Hertz. And there we go. That is the frequency observed by the listener when we have an ambulance that is moving towards the stationary listener with a velocity of 30 meters per second. Right. Our third example. An ambulance is moving away from a stationary listener. So when the ambulance is moving away, what are we going to have? Let's go back to the four equations. When it is moving away, we have plus Vs on the denominator. Right, let's go back to our equation. It's moving away with a velocity of 25 meters per second. The frequency emitted by the ambulance is 450 Hertz. Calculate the frequency that the listener will detect if the speed of sound in air is 340 meters per second. Right, we have Vs, which is 25 meters per second. We have the frequency emitted, so that is Fs, which is 450 Hertz. Calculate the frequency detected, so we want Fl, and then the speed of sound in air is 340 meters per second, and our listener is stationary, so VL is equals to 0. Right, our ambulance is moving away, so we're going to have FL being equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. Right, this is the equation without making any adjustments, and then FL is going to be equals to the speed of sound in air, that is 340, plus or minus Vs. Our listener is stationary, so we can just forget about that. And then the ambulance is moving away, so we're supposed to have plus Vs on the denominator. So that is 340 plus Vs, which is 25, multiplied by the frequency emitted, 450. So again, real quick, I just need to put that in my calculator. So let's go ahead and take a look. What is the frequency observed? The frequency observed is 419.18 Hertz, which makes sense because our sound source is moving away. So you would expect the observed frequency to be less than that which is emitted. Right. In those examples that we talked about, you can see that we have a sound source that is moving and a stationary listener. Let's take a look at this example where the listener is moving and the sound source is stationary. A car is in attendance at an accident scene. A police car is in attendance at an accident scene. The police car is stationary and its siren is emitting a sound of frequency 1000 Hz. A taxi is traveling towards the accident scene at a velocity of 23 meters per second. Calculate the frequency of sound heard by the driver of the taxi when driving towards the scene. The speed of sound in air is 340 meters per second. Right. Frequency emitted, that is 1000 Hertz. What other information do we have? We have the velocity of the listener, which is moving towards the scene, 23 meters per second. The sound source is stationary, right? Because the police car is in attendance at an accident scene, right? They even say that the police car is stationary. You would deduce it from the fact that is in attendance at the accident scene, but they do tell you either way. Right. What else? We have V, speed of sound in air, 340 meters per second. What else do we need? We want to calculate FL, the frequency observed. So we're going to have FL being equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. So what is V, speed of sound in air? 340. Our listener is moving towards. So on the numerator, we're going to have plus 23. Right, we only have 4 cases. So you should know when we have a plus, when we have a minus, and so on. On the denominator, 340. Our sound source is stationary. So it will just be 340. Plus or minus 0 doesn't matter. Multiplied by Fs, the frequency emitted by the sound source, that is 1000 Hertz. So we are expecting at least the frequency that we are expecting at least the frequency that is observed by the listener to be more than 1000 Hertz, to be more than that which is emitted, because the listener is moving towards the source. We have 1067.65 Hertz. So there we go. Our listener is moving towards the scene, so the frequency which is observed is greater than that which is emitted. So good. So far so good. And in our third case, our listener is moving away from a stationary sound source. So a siren at a fire station emits sound of frequency 780 Hz. Calculate the frequency that the driver of a car will detect if he is traveling away from the fire station at 28 meters per second. The speed of sound in air is 340 meters per second. Right, let's take a look. FL is equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. Sticking to the basics up to so far. This is the frequency, this is Fs, this is the frequency emitted. And then the speed of sound in air is 340. So we have 340 plus or minus VL. The car is moving away from the fire station at a velocity of 28 meters per second. So we're going to have minus 28 divided by 340. The source is stationary. Multiplied by the emitted frequency, which is 780 Hertz. In this situation, we are expecting the frequency observed to be less than that which is emitted. So let's go ahead and take a look and see what happens. So 780, from 780 to 715.76 Hertz. Right, you can clearly see here that the frequency observed is less than that which is emitted, because the listener is moving away from the sound source. But these examples that we touched on, they are a bit narrow in that we are always trying to calculate FL, but that's not always the case. Sometimes you're given FL, you're given Fs, and you're supposed to find out the velocity of the sound source or the velocity of the listener. Those are the nature, those are the type of questions you expect in the exam. And we're going to go ahead and take a look at that right now. Calculate the wavelength of the detected sound. That is the first question. Let's go ahead and take a look at our question statement. The siren of a stationary ambulance emits sound waves at a frequency of 680 Hz. A man is standing with a detector that records the wavelength of the sound emitted by the siren, as shown in the diagram below. The speed of sound in air is 340 meters per second. Right, so the siren of a stationary ambulance emits sound waves at a frequency of 680 Hz. And the question is saying, let's calculate the wavelength of the detected sound. If the ambulance is stationary, the detected sound will have the same frequency the ambulance is emitting because it is stationary. There is no relative motion between the sound source and the observer. So what are we going to have? We're going to have the frequency detected being equals to the velocity divided by the wavelength. So what will be the frequency detected? The frequency detected will be the same as the frequency which is emitted because there is no relative motion between the sound source and the observer. So the frequency is 680 hertz. The velocity, the speed of sound in air, 340 meters per second, and then divided by the wavelength. We're interested in the wavelength here. So if we cross multiply, we're going to get 680 wavelength being equals to 340. So the wavelength is equals to 340 divided by 680. This should be equals to 0.5 meters. So there we go. That is the wavelength of the detected sound. The frequency which is emitted by the stationary ambulance is the same frequency which is detected by the detector because the ambulance is stationary and the detector is also stationary. There is no relative motion. So the frequency emitted is the same as the frequency which is observed by the listener or which is detected by the detector in this case. That is the key to the first question. Let's take a look at the second question. The ambulance now moves at a constant speed along the road towards the man. Now there is a Doppler effect that is going to occur because the ambulance is now moving relative to the man, right? The detector now records the wavelength of the sound, which differs from the previous reading by 0.05 meters. Calculate the speed of the ambulance, right? So the wavelength has changed. It now differs by 0.05 meters. But did it increase by 0.05 meters or did it decrease? The ambulance is moving towards the man. So the wavelength decreases so that the frequency can increase. So take a look at this. The frequency emitted by the source is equals to 680 hertz. This is the frequency emitted by the source. But as for the frequency that is experienced by the listener or the frequency that is detected, we are only given the wavelength, right? Because take a look at this. The wavelength that is detected by the listener will be equals to the wavelength emitted by the source minus 0.05, because it says here that it now differs by 0.05 meters. So why are we saying minus 0.05? Because the ambulance is moving towards the man. So the wavelength should be smaller and not bigger. If it was moving away, it will be plus 0.05. But here it is moving towards. So it's going to be minus so that we can have a shorter wavelength and a higher frequency. Right. So the initial wavelength, we know that it was 0.5. So 0.5 minus 0.05, this is 0.45 meters. So that is the wavelength that is experienced by the listener, which is detected by the detector, right? So from this wavelength, obviously, we can go ahead and find the frequency which is experienced by the listener, the frequency observed, right? What other variable do we have? We have V, speed of sound in air. This is a constant. So, well, let me not say it's a constant, but it is given to us, right? It is not always 340 meters per second. If I say it is a constant, there might be that misconception that it must be always 340, but it's not. And then we have the velocity of the detector. Well, the velocity of the man. The man is stationary. So VL is equals to 0. And then we are looking for the speed of the ambulance. We are looking for VS. What is VS? Right. So take a look at this. We're going to have our equation. FL is equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. So we have V, we have VL, we have Fs, we are looking for Vs, but we still don't have FL. We still don't have FL. So let's just go ahead and calculate FL. So in order to calculate FL, we're going to say that FL is equals to, so frequency is velocity divided by wavelength, right? We have the velocity, which is 340, and then the wavelength, which is 0.45. So we can go ahead and substitute that in place of FL. So in place of FL, we have 340 divided by the wavelength, which is 0.45. This is equals to the velocity, the speed of sound in air, not the velocity. We talk about speed in Doppler effect. So 340, the listener is stationary, so plus or minus 0 is not going to change anything, divided by 340. The ambulance is moving towards the man, so we should have minus Vs. If it was moving away, we would have plus Vs, multiplied by the frequency that is emitted. This is 680 Hz. So at this point, we are done with the physics. We just need to solve the math. But a lot of people still make a mistake, even if they manage to get to this point. Okay, let's just say 340 divided by 0.45. That is 755.5555. Let me drag this up here. So we're gonna have 755.5556 being equals to 340 divided by 340 minus Vs multiplied by 680. So now I can divide both sides by 680, right? So let me divide here by 680 and also divide here by 680. So 680 and 680 would cancel out. On the left hand side, I'm left with 1.1111 being equals to 340 divided by 340 minus Vs. So we can rearrange this and have 340 minus Vs being equals to 340 divided by 1.1111. So I'm getting 340 minus Vs being equals to 306. So minus Vs will be 306 minus 340, which is minus 34. If we divide both sides by minus 1, Vs should be equals to 34 meters per second. Does the detector record the frequency of 30,148 Hz when the train moves towards the detector or away from the detector? That is the first question. Let's go ahead and take a look at our situation. The siren of a train moving at a constant speed along a straight horizontal track emits sound with a constant frequency. Right, you have a train, it is moving and it's emitting sound at a constant frequency. So the train is our sound source, right? And then a detector placed next to the track records the frequency of the sound waves. Okay, that is our listener, and the results obtained are shown in the graph below. You can see that this graph that we have in this situation is different from the graph we had previously. So let's analyze this one and make sense of what is happening. So the time in seconds and the frequency that is recorded on the y-axis, right? So here we have a frequency of 30,148 Hz, and after some time the frequency recorded is 2,073 Hz. Why is that the case? Here where we have a higher frequency, that's where the train is moving towards the detector, and here where we have a lower frequency, the train is moving away from the detector. This makes sense because we know fully well that if a sound source is moving towards the listener, we have a higher frequency, and then when it is moving away, we have a lower frequency. So does the detector record the frequency of 3148 Hz when the train moves towards the detector or away from the detector? When the train moves towards the detector, because we have a higher frequency, and then 2043 Hz when it is moving away from the detector. Let's take a look at the question that follows. Calculate the speed of the train. Take the speed of sound in air as 340 meters per second. So I need you to pay attention to this part. Right. So let's take a look at this. When the train is moving towards, we have a frequency of 3148 Hertz. So let's see if we can use that to calculate the speed of the train. The frequency which is observed, FL, is 3148 Hertz. This is when the train is moving towards. Right. And then the frequency which is emitted, FS, is not given to us, so we don't have that. And then our observer is stationary, the detector. So we have VL being equals to 0. We're interested on VS, the speed of the sound source, the speed of the train. And then the speed of sound in air is given to us as 340 meters per second. So we know fully well that FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So FL, when the train is moving towards, that is 3148. This is equals to speed of sound in air, 340. Our listener is stationary, like we've said. So plus or minus 0 doesn't make a difference. Divided by V plus or minus VS. So what is the speed of the sound source? That's what you're interested in. 340. We know that it is moving towards when the frequency is 3148. So we're going to have minus VS multiplied by the frequency of the source, which we don't have. So this is what we have. As you can see, we have two variables, VS and FS. In a situation like this, you should always remember that you just need one other equation because you have two unknown variables. After you get another equation, it's a matter of solving simultaneously. So this becomes our equation 1 because we have two unknown variables. And then now let's take a look at the case where it is moving away. When it is moving away, the frequency observed is 2073. And then speed of sound in air, 340. And then on the denominator, we're going to have 340 plus VS. It's plus because now it is moving away. And then again, we don't know what FS is. And then this is our equation 2. So we can use these two equations to find VS, the speed of the train. So how can we do that? Right, we can make FS the subject of the formula on the first equation and make FS the subject of the formula on the second equation. After we do that, we're gonna then be able to equate the two equations. Our only unknown is FS, and we solve. We can make FS the subject of the formula on the first equation by dividing both sides by its coefficient. We're dividing both sides by this in order to make FS the subject of the formula. So on the first equation, we're going to have 3148 divided by 340 divided by 340 minus VS. This is equals to FS in our equation 1. And then in our second equation, we're going to have 2073, everything divided by 340 divided by 340 plus VS. This is equals to FS. So these two things are equals to FS. So we can just equate those two. You can see that we were supposed to have our equation 3 here, But for the time being, let me just erase it and continue solving question 2, because it seems like we're gonna need a little bit more space. So let's carry on with question 2. So we are equating the two equations. The first equation, that is 3148 divided by 340, everything divided by 340 minus Vs. This is equals to 2073 divided by 340 divided by 340 plus Vs. Right, yeah, the physics is done here. We just solving the math equation, to be quite honest. So how can you solve this? Let's start by cross multiplying. Right, so if you cross multiply, I'm gonna get 30,148 multiplied by 340 divided by 340 plus Vs. This will be equals to 2073 multiplied by 340 divided by 340 minus Vs. So let's go ahead and put these numerator on our calculators. So 30,148 multiplied by 340. This is 50,300 and no, that is wrong. I substituted the wrong thing. Right, let me put it in scientific because I'm getting a very big number. So scientific, when I do that, I'm getting 1.0703 times 10 to the power 6. Right, divided by 340 minus plus Vs. This will be equals to, so now 2073 multiplied by 340. This is 7.0482 times 10 to the power 5. Everything divided by 340 minus Vs. Again, we need to cross multiply. So we have 1.0703 times 10 to the power 6 multiplied by 340. I'm getting 3.6390 times 10 to the power 8 minus 1.073703, not 73, 03 times 10 to the power 6 Vs. I just multiplied this with this. Right, now I need to multiply this with this. So let me go ahead and do that. That will all be equals to, so 340 multiplied by 7.0482 times 10 to the power 5. So this is 2.3964 times 10 to the power 8, and then plus 7.0482 times 10 to the power 5. So right, let me group the like terms together. This is Vs, right? So I'm gonna take this term to the right hand side and take this to the left hand side. If I do that, I'm gonna have 3.6390 times 10 to the power 8 minus 2.3964 times 10 to the power 8 being equals to 7.0482 times 10 to the power 5 Vs plus 1.0703 times 10 to the power 6 Vs. So let me put the left hand side of my calculator. 3.639 times 10 to the power 8 plus 2.3964 times 10 to the power 8. We have minus here. Let me put that in my calculator. I'm getting 1.2426 times 10 to the power 8 being equals to 7.0482 times 10 to the power 5 plus 1.0703 times 10 to the power 6. This is 1.7751 times 10 to the power 6 Vs. So I need to divide both sides by the coefficient of Vs. So 1.2426 times 10 to the power 8 divided by 1.7751 times 10 to the power 6. I'm getting Vs being equals to 70.00 meters per second. So there we go. That is the speed of our train. After doing this much work for this question, I'm not even sure you'd still be interested on that third question that I was talking about. But this third question was saying, let's calculate the value of T1. So you go ahead and do that and tell me which answer you get. This was a very long question, not difficult, but long because we had to do all of this. So I recommend that you actually watch this part again because we did a lot of things here. But anyway, I'll see you on the next video where we tackle a situation that is different from this one. Use the graph to answer the following questions. Let's go ahead and take a look. So we have a learner in a car moving at a constant velocity of 10 meters per second along a straight horizontal road. The learner records the frequency of sound emitted by a distant stationary source. The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. The graph below, not drawn to scale, is obtained from the results. So let's go ahead and analyze this graph. On the x-axis, we have the speed of the car in meters per second. And then on the y-axis, we have the recorded frequency or the frequency experience. That will be FL, the frequency observed by the listener. So let's analyze this graph. When the speed of the car is 0 meters per second, the frequency recorded is 700 hertz. We're going to come back to that. And then when the speed of the car is 10 meters per second, the recorded frequency is 679.1 hertz. And then when the speed of the car is 20 meters per second, the recorded frequency is 658.2. Right, so let's make sense of this frequency when the speed of the car is 0 meters per second. When the speed of the car is 0 meters per second and our source is stationary, there is no Doppler effect. The frequency or the pitch observed doesn't change, right? So this 700 hertz that we have here, it's actually the value of Fs, the emitted frequency, because it's the frequency we have when the speed of the car is 0 meters per second. So this is actually the key to this question. As soon as you understand that, then all the other problems that come are quite easy to solve, right? So this video is one of 4. In this little experiment that we have, you had to realize that you're given Fs. And then in the other questions that we're going to be solving soon, there's going to be different tricks. So that's actually what I want us to go through. How do we interpret a question when we are given a graph or when we are given a table with data on it? That is the skill I want to teach you, because most of the time with Doppler effect, you're going to come across a situation that you've never seen before, and you have to be able to analyze that situation. Let's take a look at the first question. Write down the frequency of the sound emitted by the stationary source. Give a reason for the answer. Well, we have talked about that. We know that the frequency emitted by the source is 700 hertz. And why do we say that the frequency emitted by the source is 700 hertz? Because that is the frequency recorded when the speed of the car, velocity of the listener, is equals to 0 meters per second. And the velocity of the source is also equals to 0 meters per second. When this is the case, when the listener is stationary and the source is stationary, there is no Doppler effect taking place. There's not going to be a change in the frequency observed. So that is why we are saying that the frequency emitted by the stationary source is 700 hertz. As soon as you realize that, everything else becomes doable. The second question, in which direction is the car moving relative to the source? Choose from towards or away. Give a reason for the answer. So, right, again, we need to answer this question basing it on the graph that we have. So take a look at this. I'm not sure if you realize, but when the speed of the car is 10 meters per second, the observed frequency is 679 hertz. And then when the speed of the car increases to 20 meters per second, the observed frequency is 658. So as the speed of the car increases, the observed frequency is decreasing. So clearly the car is moving away because of that. If it was increasing, the car would be moving towards. So what are we saying? In which direction is the car moving relative to the source? It is moving away. Why do we say that? As the velocity of the listener increases, FL decreases. So the listener has to be moving away from the source if that is the case. Right, as the velocity of the listener increases, FL, the observed frequency, decreases. That is question 2. Let's go ahead and take a look at the third question. Calculate the speed of sound in air. Right, calculate the speed of sound in air. So we know that we are looking for V. We know fully well that Fs is 700 Hz. That is the emitted frequency by the source as it is. And then what else do we have? Let's go ahead and take a look. So we have 2 data points we can use. Say that you can use these first data point or you can use the second one. Because if you use this point, you have FL and its corresponding VL. And then if you use the second point, you're going to have FL and its corresponding VL. So whatever point you decide to use between these two, you're going to get to the same answer. Right. So let's use these very first point. Let's use this point here. So if we use that point, then we would have FL being equals to 679.1 Hertz. That is the observed frequency. And speed of the car, so that is VL, because it is the listener that is moving in a car, right? So VL will be 10 meters per second. And then Vs is equals to 0. We know that our source is stationary. So with this data, we can then use FL is equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. We know fully well that our listener is moving away. So if it's our listener is moving away, we're going to have V minus VL divided by V. Our source is stationary, so plus or minus 0. It's not going to really change anything. Multiplied by Fs. Right, here on the numerator we have minus because our listener is moving away. We can go ahead and substitute now. FL, the frequency observed, we have 679.1 being equals to speed of sound in air, so that is V minus the velocity of the listener, 10 meters per second. Everything divided by V, multiplied by the frequency emitted. So there we go. We have solved the physics question. Right now we're just solving for V. It now becomes a mathematical problem. Let's divide both sides by 700. If you divide on the right hand side by 700, 700 and 700 will cancel out. So we're gonna have 679.1 divided by 700 being equals to V minus 10 divided by V. Let's go ahead and cross multiply. So 679.1 V is equals to, we are multiplying 700 with that, right? So 700 V minus 7,000, right? So let's take this to the left hand side. So I just need to put that in my calculator. 679.1 minus 700, that is minus 20.9. So minus 20.9 V is equals to minus 700. So V is equals to Minus 700 divided by answer will give me, hey, I was getting surprised. This is minus 7,000. Minus 7,000. Here it is. We bring it here and we take this to the left hand side. Right, so it is minus 7,000. I was surprised. My answer was not making any sense. So V is equals to 334.93 meters per second. And there we go. We have our speed of sound in air. Calculate the frequency of the sound emitted by the siren. Let's go ahead and take a look. The siren of a stationary ambulance emits a note with a wavelength of 0.3 meters. While the ambulance moves at a constant velocity, a graph is drawn from the data recorded by a detector placed next to a road a distance away from the ambulance. Take the speed of sound in air as 340 meters per second. Right, let's go back to our question and see how we can possibly answer it. Calculate the frequency of the sound emitted by the siren. The only information we have with regards to the sound emitted by the siren is the wavelength. We know that the wavelength emitted by the siren is 0.3 meters, right? The wavelength of the sound emitted by the siren. So that is the wavelength, 0.3 meters. Another piece of information we have is the speed of sound in air. So V is equals to 340 meters per second. We are interested in the frequency. What is the frequency of the sound emitted by the siren? Well, most people will get this right, but some people will actually get it wrong. We know from grade 10 that the frequency is equals to the velocity divided by the wavelength. So this is the very equation we're going to use in this question, right? So if you just forgot about all the knowledge from previous grades, you probably get this wrong. And if you get that question wrong, then issues are gonna arise with the second question because we probably are going to use that field. So the velocity, 340 meters per second, and then the wavelength, it's said to be 0.3 meters. So 340 divided by 0.3, I am getting 1133.33 hertz. This is the frequency of the sound emitted by the siren, our Fs. Let's take a look at the question that follows. Calculate the speed at which the ambulance is traveling. Right, is the ambulance moving towards or away from the detector? We're not even sure of that, but let's just write down the information we have first and see how we're gonna tackle this problem. Well, we know that the frequency Fs, frequency emitted, has a frequency of, we know that the frequency emitted by the siren is 1133.33 hertz. We have speed of sound in air, so V is equals to 340. Do we have the velocity of the listener, the velocity of the detector, or is it stationary? Recorded by detector placed next to a distance. Detector placed next to the road at a distance. So VL, the velocity of the listener or the detector, is 0 meters per second. We're interested in VS, the velocity of the source. We still need FL and need to figure out whether the ambulance is moving away or towards the detector. But we have a graph here, and that's what we are going to use. Like I said, the series, these videos that I'm making, they are based on different situations you can come across in the exam and how to navigate through. So let's read our question first and see how this graph helps us. The siren of a stationary ambulance emits a note with a wavelength of 0.3 meters, while the ambulance moves at a constant velocity. A graph is drawn from the data recorded by a detector placed next to a road a distance away from the ambulance. A graph is drawn from the data recorded by a detector. So We can find FL from this graph because it is drawn from the information recorded by the detector. So that is actually the key to this question. Right, let's go ahead and take a look and see how we can possibly answer this question. Okay, FL, we know that the frequency is equals to 1 over t, right? I'm choosing this equation because of the graph I have. On the x-axis, I have the time, and then on the y-axis, I have the air pressure. So that's why I want to calculate the frequency using 1 over t, because I can extract the period. We know that the period is the time taken for one complete wavelength. So from A to B, it's one wavelength. And then from B to C, it's another wavelength, right? So from A to B is 8 times 10 to the minus 4 seconds. And then from B to C, it's another 8 times 10 to the minus 4 seconds. So that is our period. Our period is 8 times 10 to the minus 4 seconds. It actually says times 10 to the minus 4 seconds here. So if you miss that and you use 8 seconds, then again, you're not going to be able to answer this question. So the frequency, let's go ahead and substitute. It will be 1 divided by 8 times 10 to the minus 4. So let me just go ahead and put that in my calculator. I'm getting 1250 hertz. So this is the frequency emitted, and this is the frequency observed. So let's take a look at the frequency emitted and the frequency observed. The frequency observed, FL, is greater than the frequency emitted. So obviously, the ambulance has to have been moving towards the detector. That is the only way FL can be greater than FS. So what are we saying? We're saying that FL, now that we have our variables, V plus or minus VL divided by V plus or minus VS multiplied by FS. So let's go ahead and substitute. FL, 1250 being equals to V, the speed of sound in air, that is 340. Our listener is stationary, plus or minus 0, divided by 340. The sound source is moving towards. When the sound source is moving towards, we have minus. So minus VS multiplied by FS. FS, frequency emitted, 1133.33. So right, you can see now that we have solved the problem, right, as far as the physics is concerned. Now it's just a matter of solving the mathematics behind it. Right, I'm doing that because I'm running out of space. So let's go ahead and divide both sides by this number. If we do that, we're going to have 1250 divided by 1133.33 being equals to 340 divided by 340 minus VS. So let me go and divide those numbers on the left hand side, or I can just cross multiply at this point, right? Whatever method you really use to solve for VS, there's no issues. We can use different methods, but we will get to the same answer if we don't make an error. So right, if we cross multiply, we're gonna have, is that 385,000, right? 385,000, 332.2 being equals to 1250 multiplied by 340. So 425,000 minus 1250 VS. So I'll take this to the left hand side, obviously. So 385,000, 332.2 minus 425,000. That is minus 39,667.8 being equals to minus 1250 VS. So I just need to divide both sides by the coefficient of VS. When I do that, I get VS being equals to 31.73 meters per second. That is the speed of the ambulance. I'll see you on the next video. there is also another problem which is unique to this one and the one we have solved previously. So let's go ahead and take a look at that. One of the most interesting questions under Doppler effect I've came across, that is 6.1.2, right? So let's look at 6.1.1. You just need to state the definition of Doppler effect in words, right? I'm sure you can do that. Let's look at 6.1.2, the interesting question. So the question is saying a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits sound waves with a frequency of 24,000 Hz. Alright. And then these sound waves are reflected off the car, and the reflected sound waves are then detected by the device as shown in the diagram below. We can see what is happening there. And then if the speed of sound in air is 340 meters per second, let's calculate the frequency of the reflected sound waves detected by the device. So let's do a bit of conceptualization here. So let's put X as our vehicle and put our device somewhere here. So the first thing that is going to happen, our device is emitting a sound wave, right? So let's just denote that. So we have some frequency of source, and then when it strikes the car, it's no longer Fs. We now have FL, right? It's going to is going to detect a totally different frequency, and then from that frequency it detects, it's now going to reflect it and send it back to the device. So now we have this frequency being reflected back to the device, and then now we have FL2. So you can use this Fs here to find FL, and then when you find that FL, it now becomes your Fs that the device is going to detect. Am I making any sense? Let me show you what's going on. So for the first part, we have the frequency of the listener being equals to V plus or minus the velocity of the listener divided by V plus or minus the velocity of the source multiplied by the frequency emitted by the sound source. Right. So the frequency observed by the listener, or the frequency that strikes our vehicle, it will be equals to 340, and then our listener or our vehicle is moving towards the device, right? So we're supposed to have plus the velocity of our listener, which is 22 meters per second, and then we can divide everything by 340 plus or minus the velocity of the device, which is 0, right? It is stationary, and then we can multiply that by the frequency emitted by our device, which is 24,000. Right, so let me just compute that real quick. So I have 340 plus 22 divided by 340, essentially multiplied by 24,000, and I'm getting 25,552.94 Hertz. So this is the frequency that strikes our car. This is the frequency that strikes our car. And now this frequency is reflected back to the device as Fs, right? This frequency now becomes our Fs, is reflected back to our device. So what am I saying? We're saying that now we're going to have FL being equals to V plus or minus VL divided by V plus or minus Vs multiplied by the frequency emitted by the source. So what is FL? FL is what we're looking for, the frequency that is detected by the device, right, after it has been reflected. Right, that will be equals to 340, and then now our listener is the device. We know that it is stationary, so we're gonna have plus or minus 0 divided by 340, and then now our sound source is moving towards, it is the car, right? So we're gonna have 340 minus 22 multiplied by the frequency of the source, which is what we calculated here, 25,552.94 hertz. That is the frequency that is being reflected by the car. This is the trick of the question. As soon as you can wrap your head around the concept, then you're essentially done. So multiplied by 25,552.94 hertz. I'm getting 27,320.75 hertz. Right, so that is the frequency of the reflected sound waves detected by the device. Right, and the last question, 6.2, the spectral lines observed for a distant star show that the star is moving away from Earth. Explain by referring to frequency how one can deduce that the star is moving away from the Earth. So here I'm much interested in how you guys answered this question. So can you please just let me know in the comment section. State the Doppler effect in words. Of course, we're going to skip that. Let's do 6.2. Use the information given to calculate the speed of sound in air. Mark allocation, 5 marks. So let's go ahead and take a look. A stationary listener records the frequency of the sound emitted by the siren of a police car. When the car, which is traveling at a constant velocity, so we have the velocity of the source right away. So Vs is 26 meters per second. Approaches the listener, the recorded frequency is 615 hertz. So the velocity, not the velocity, but the frequency that the listener records, the frequency observed, is 615 hertz. This is when the car is moving towards. The car passes the listener at t is equals to 1. At time t is equals to 1. Okay, right. And then moves away from the listener. The recorded frequency is now 526 hertz. So this is towards 615. And then when it is moving away, we have Fs, not Fs, but Fl, which is 526 hertz. Use the information given to calculate the speed of sound in air. Okay, not quite sure how we're going to do this one, but take a look at this. Let's stick to the basics. Let's start with this case where the kite is moving towards. So we're going to have Fl being equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. This is the formula as it is before we do any modification. You get a mark for the formula. Now we can modify it. Fl is equals to V is the listener stationary, a stationary listener. So the listener is stationary. So we just have V divided by V plus or minus Vs. So we have V, speed of sound in air, of which we're trying to calculate. And then Vs, that of the source. The source is moving towards, right? So we're going to have minus 26 multiplied by the observed, multiplied by Fs. We know Fl, when the listener, when the sound source is moving towards, it is 615 hertz. So we're going to have that there. So there we go. We have these. We can't proceed anymore because we have two unknown variables. Let's take a look at the case where it is moving away. When it is moving away, the observed frequency, okay, the observed frequency is 526 hertz. And then we have V divided by V. Now that it is moving away, you're going to have plus 26 multiplied by Fs. Fs is all the same because that is the emitted frequency. So we have these two equations. We have this equation 1 and this equation 2. And what we need to do is to solve simultaneously. That's what we need to do. So how can we possibly do that? Well, we have two unknown variables. So it's either we make Fs the subject of the formula in equation 1 and substitute in F2, or we can, what else can you do? We can make V subject of the formula in equation 1 and substitute in equation 2. Whatever we decide to do, it's all going to work out. So let's take a look and see which one is the easier case here. Can we easily make fs subject to the formula in equation 1? I think so. Let's take a look at what we can do. So with equation 1, we're going to say 615 everything divided by v minus 26. This is equals to fs. We're just dividing everything by the coefficient of fs. But we can switch that division into a multiplication, right? If you are dividing by a divided by b, is the same as multiplying by b over a. So we can apply that idea to get over that hurdle. So let's go ahead and do that. 615 multiplied by v minus 26 divided by v. We can write it like this instead, and this is fs. Okay, let's further simplify it. 615 multiplied by v is 615v, and then we have 615 multiplied by minus 26, that is minus 15,990 everything divided by v, right? This is fs. So let's substitute these fs into our equation 2. Okay, so if we do that, can we take this to the left hand side first? Can we take that to the left hand side first? Okay, let's take that to the left hand side first. If we take that to the left hand side first, we're going to have 526 multiplied by v plus 26 divided by v. We are applying what we applied on the first equation. Obviously, let's multiply out before we substitute fs. So 526 multiplied by v is 526v, and then plus 26 multiplied by 526. That is, oh, okay, here we have v, here we have v, and then plus 13,676 everything divided by v. This is equals to fs. Now, in place of fs, we're gonna then substitute these which we have here, right? So in place of fs, we're gonna substitute 615v minus 15,990 everything divided by v. Think we're getting somewhere. Because we are dividing on the left side by v and dividing on the right side by v, we can just drop v, because the numerators must be equals to each other for those two things to be equals to each other. So right, we're just gonna have 526v plus 13,676 being equals to 615v minus 15,990. I think it's quite simplified now. Let's take these to the left hand side. So 526 minus 615, that is minus 89v being equals to minus 15,990 minus 13,676. That is equals to minus 29,666. So v is equals to, we divide that by minus 89. Let's take a look. I'm getting 333.33 meters per second. That is not a bad value of the speed of sound in air. It is not alarming. If we were getting something like 1,000, we would be very surprised. Or if we're getting something like 200, we would be very surprised. So the math that I applied here, I mean, it is not the only way you can solve this question, right? The concept is the same, but then the math can be completely different depending on which variable you are making the subject of the formula, so on and so on. But essentially, at the end of the day, we should get the same answer. That is 6.2. 6.3, calculate the wavelength of the sound emitted by the police siren. Okay, we want the wavelength of the sound emitted by the police siren. That is out of 4 marks. So the siren emits fs. This is what the siren emits. And then v is 333.33 meters per second. So we have v. We are looking for the wavelength. So v is 333.33 meters per second. Fs, we can calculate it, but at this point we don't have it. So how are we going to calculate Fs? We have this equation here, so we're going to use that equation to calculate Fs. So Fs is equals to 526 multiplied by V is 333.33 plus 26 divided by 333.33. So let me put that in my calculator. 526 multiplied by 333.33 plus 26, everything divided by 333.33. Right. And then when I put that in my calculator, I get 567.0284 watt hertz. I can actually prove if this is correct, but I don't think it's necessary. I'm quite sure this is correct. Okay, so we have Fs. So now we just need the wavelength. The frequency is equals to the velocity divided by the wavelength. So the wavelength is the velocity divided by the frequency. So let's substitute here. 333.33 divided by 567.0284. Okay, 333.33 divided by 567.0284. This is 0.59 meters. So there we go. We have the frequency. Now 6.4. Sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away from the listener. Label the time t1 on the graph. No values needed to be indicated on the frequency axis. Okay, so let's take a look. First of all, we need the frequency axis. So there we have it, and then we have the time axis. So let's take, what am I doing? Right, so this is the time in seconds, and then this is the frequency in hertz. Have you heard? We don't need to include any values. Okay, so initially, is it moving away? It approaches initially, right? And then after that, it passes and moves away. So when it is approaching, we have a higher frequency. So somewhere here, this is our frequency when we are approaching. And then something happens at T1, right? Something happens at T1. At T1, it passes the listener and it's now moving away. So we are expecting something like this. The frequency is going to decrease. The frequency is going to decrease. I was supposed to indicate something. Sketch the graph as it moves towards. Okay, I don't know. It doesn't say we must indicate which one is towards. But here, this is towards. As it is moving towards. This is away. And then somewhere in the middle here, we have the emitted. There we go. Name the phenomenon that explains why the wavelengths shown in the graph differ. I think all the time in question 6, when we come across something like this, we know what the answer is already. Doppler effect. And then question 6.2 is the car moving towards or away from the listener. Give a reason for the answer. Now we have to go through the question statement. A stationary listener standing on the roadside records the wavelength of the sound emitted by a siren of a police car traveling at a constant velocity. In the wavelength time graph below, not drawn to scale, wavelength of the listener is the, wavelength with the subscript of L, right, is the wavelength of the sound recorded by the listener, while the one with a bit of an S here is the wavelength recorded by, the wavelength of the sound emitted by the siren. And then we're supposed to take the speed of sound in air as 343 meters per second. So is the car moving away or towards the listener? The listener is stationary. So what is influencing the wavelength that the listener observes is the motion of the car, whether it is moving away or towards. So take a look at this. The frequency of the listener, or not the frequency, but the wavelength observed by the listener is greater than the wavelength observed by or emitted by the sound source. But wavelength and frequency is inversely proportional to the wavelength, right? So this simply implies that the frequency emitted by the source is greater than the frequency observed by the listener. So if the frequency observed by the source is if the frequency emitted by the source is greater than the frequency observed by the listener, what does that imply? It implies that the listener has to be moving away, given that the sound source is stationary. So that is the answer to 6.2. And then 6.3.1, calculate the frequency of the sound emitted by the siren. Well, we have the wavelength of the sound emitted by the siren, so it should be quite easy to calculate the frequency. F is equals to V divided by the wavelength. We are told that we are supposed to take the speed of sound in air as 343 meters per second. So we have 343 divided by 0.38. It's already in meters, so we don't have to change anything there. So 343 divided by 0.38. This gives us 902.63 hertz. This is the frequency emitted by the source. 6.3.2, magnitude of the velocity of the car. That is actually the last question in question 6. So we are looking for the velocity of, well, the car. Is the listener the one who is stationary, or the car is the one that is stationary, our sound source? Let's go through our question statement again. A stationary listener. Okay, so the listener is stationary. So the listener is stationary. It is the car that is moving away, right? So the answer here is still away, but it is actually the sound source that is moving and not the listener. The listener is stationary. It's the sound source that is moving away. Okay, so magnitude of the velocity of the car. So this is the velocity of the sound source that you are looking for. We have the frequency of the sound source because we have calculated it. We have the velocity of, well, the speed of sound in air. It is given to us. Velocity of the speed of sound in air, it is just V. It is given to us, right? Magnitude of the velocity of the car. So we are looking for Vs. We have VL because the listener is stationary, which is 0. And then what about the frequency observed by the listener? We can calculate that because we are given the wavelength, right? Not the we are given the wavelength, but we can calculate the frequency. It is going to be equals to 340. Well, okay, let's leave that for now, but we can calculate it, right, as we move forward. So with these variables, we can say FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So FL, the frequency observed by the listener. So we're gonna say 343 divided by the wavelength, right, which is 0.4. So this is the frequency observed by the listener. And then we have V, which is 343. The listener is stationary, so plus or minus 0. And then we have 343. The sound source is moving away, so we're gonna have plus VS multiplied by the frequency emitted by the sound source, which is 902.63. So 343 divided by 0.4, this is 857.5, and it is equals to 343 divided by 343 plus Vs multiplied by 902.63. Let's divide both sides by 902.63. If we do that, we're going to get 0.95 being equals to 343 divided by 343 plus Vs. Let's cross multiply. So 0.95 multiplied by 343, this is 325.8506, right? And then plus 0.95 Vs. This is equals to 343. So Vs is going to be equals to 343 minus 325, 32, not 3, 32.5, 325.8506, everything divided by 0.95, the coefficient of Vs, right? So let me just put that in my calculator and see what I get here. I'm getting 18.05. So Vs is 18.05 meters per second. There we go. That is question 6. So we have done question 2, 3, 4, 5. If you haven't watched that, click on the channel and you'll find those videos. Which question do we go to next? Let me know in the comments. Here we go. 6.1.1 state the Doppler effect in words. Well, I'm just going to leave that one to you and go straight to 6.1.2. A physics learner clock radio awakens her with a steady and irritating sound of frequency 600 Hz. One morning it malfunctions and cannot be turned off. In frustration, the learner drops the clock radio out of a 4th-story dorm window 15 meters from the ground. Assume that the speed of the sound is 343 meters per second. Ignore the effects of air resistance. Calculate the frequency that the learner hears just before the clock radio strikes the ground. So the frequency observed by the learner will be equals to V plus or minus VL divided by V plus or minus Vs multiplied by the frequency of the source. Frequency of source, we have 600, so there is no problem there whatsoever. And then V, the speed of sound in air, it is given to us 343 meters per second. The velocity of the listener is stationary. The listener is in her room. So we have that it is equals to 0. I think what we need is the velocity of the source. We want the velocity of the clock before or just as it strikes the ground. Let's gather our information and see which equation we need to use. We have the displacement, which is 15 meters. We have our acceleration, obviously, 9.8. We have VI, which is equals to 0, because the learner dropped the clock. And what else do we have? I think that is all we need. We are looking for VF. So the simplest formula here to use should be VF squared is equals to VI squared plus 2A delta Y. So VF squared will be equals to VI, that is 0. So we have 0 squared plus 2 multiplied by the acceleration. Let's take up as positive. So our acceleration will be minus 9.8 and delta Y will be minus 15. And if we take square roots on both sides, we're going to get VF being equals to 17.15 meters per second. And just like that, we have the velocity of the sound source. So we can go ahead and substitute now. FL is equals to 343 plus or minus 0 divided by 343 plus the velocity of the source. The source is moving away, so we're supposed to have a plus sign on the denominator. So plus 17.15. Everything multiplied by the velocity of the source, which is 600 Hz. If you put that in your calculator, you should get 571.43 Hz. You need to be comfortable with doing this on Doppler effect because it is a very common trend that I'm seeing. We have to calculate VS or VL these days, some way, somehow, before we substitute into FL. It is a new trend that I'm starting to see. So let's be vigilant. Let's go ahead and find more problems that involve these kind of situations and familiarize ourselves with such. 6.1.3. Explain the change in frequency observed by the listener with reference to the speed of the radio clock. So as the clock is going down, obviously, under the influence of gravity, then the velocity of the source is increasing. We know fully well that the frequency observed by the listener is equals to V divided by V plus Vs multiplied by the frequency of the source. So if Vs is increasing, then FL should be decreasing. The frequency observed by the listener should be less than that emitted by the sound source. 6.2. A helium line from the spectrum of the sun has a frequency of 6.2 times 10 to the power 14 Hz. the frequencies of the same helium line from the Earth, which observed in the line emission spectrum of two stars, are: for star X, we have 6.24 times 10 to the 14 hertz, and for star Y, we have 6.04 times 10 to the power 14 hertz. Yeah, this is an interesting one because instead of having the wavelength, we are given the frequencies of distant stars. Usually it is wavelength, so it is quite, an interesting question. 6.2.1, which one of the stars, X or Y, has a redshift? So the one with a smaller frequency has a redshift because it has a higher wavelength. So that is star Y. And 6.2.2, in which direction, away from the Earth or towards the Earth, does star X move? Star X has a higher frequency than our reference point, 6.2 times 10 to the power 14 hertz. So it should be moving towards the Earth. 6.1.1, state the Doppler effect in words. I'm just going to leave that for you. Let's take a look at 6.1.2. Use the given information to calculate the speed of sound in air. So let's take a look at the information we have. So an ambulance is moving away from a stationary listener. So if the listener is stationary, then we have VL, the velocity of the listener, being equals to 0. Okay, the ambulance is moving away from the stationary listener with a constant velocity of 25. So we have Vs, the velocity of the source, being equals to 25. Okay, the siren of the ambulance emits sound waves at a frequency of 550 hertz. So we have the frequency as emitted by the source being 550 hertz. The siren of the ambulance, okay, 550 hertz. Let's carry on. The listener detects the frequency of these sound waves to be 512.64 hertz. So the frequency as observed by the listener is 512.64 hertz. Okay, we are told that the ambulance is moving away. But even if the question didn't say that the ambulance is moving away, we would be able to deduce it from the mere fact that the frequency of the listener is less than that of the source. But anyway, stories. So V, which is the speed of sound in air, what we're interested in, we don't have that. Okay, so that is our unknown variable. Sticking to the basics, we're going to have FL, the frequency observed by the listener, being equals to V plus or minus the velocity of the listener, V plus or minus the velocity of the source, multiplied by the frequency as emitted by the source. The frequency experienced by the listener is 512.64, being equals to speed of sound in air, what we're interested in, plus or minus the velocity of the listener. The listener is stationary, so VL is equals to 0. Everything divided by V. The ambulance is moving away, so that is supposed to be plus 25 in the denominator. If it was moving towards, it will be minus 25, multiplied by the velocity, not the velocity, but the frequency of the source. That is 550. Okay, so a mark for the formula, a mark for the substitution. Usually it's 2 marks for the substitution. They find a way to somehow squeeze 2 marks for the substitution. But let's forget about that and focus on the problem solving. Okay, so there's a couple of different methods people will use in this position, but ultimately we must get to the same answer. So this is the method I'm going to use. I will divide both sides by 550. Okay, so 550 and 550 will cancel out on the right hand side, and then on the left hand side I'm gonna have 512.64 divided by 550, which is 0.9321. So I have 0.9321 being equals to V divided by V plus 25. I didn't do anything fancy here. I just divided both sides by 550. Okay, and now I want to go ahead and cross multiply. V multiplied by 0.9321 will be 0.9321 V. Okay, and now I have 0.9321 multiplied by 25. That is going to be plus 23.3018. Okay, I'm rounding off to 4 decimal places because I'm not at the final answer. At the final answer, I'm going to round off to 2 decimal places, not 1. Okay, and then V multiplied by 1, it is just a V. If I take 0.9321 V to the left hand side, to the right hand side, I'm going to have 1 minus 0.9321, which is 0.0679. So I have 23.3018 being equals to 0.0679 V. It is obvious what I'm going to do at this point. I'm going to divide both sides by the coefficient of V, which is 0.0679. Okay, if I do that, I'm getting 343.18 meters per second. I'm quite happy with this answer because this is the value we usually get. We have 343. It's always somewhere there. Okay, so it is not unusual. It is not odd. If I was getting 20 meters per second or 900 meters per second, I would be panicking. But now I have 343, which is almost the value I always get in other problems. Okay, that is 6.1.2. 6.1.3, a bit conceptual. The ambulance is now moving away from the listener with a velocity that is greater than 25. Okay, how will each of the following change? Choose from increase, decrease, or remain the same. Let's take a look. A, the speed of sound in air. The speed of sound in air will remain constant, right? The speed of sound in air is not a function of how fast the velocity of the source is, right? So this will remain the same, okay? And then B, the frequency of the sound waves emitted by the siren. If you are emitting sound waves with a frequency of 500, that is not dependent on how fast you're moving. The frequency that you're emitting is going to be 500, whether you're stationary, whether you're moving towards, whether you're moving away. So again, we have remained the same, right? So this is the remains the same. Now let's look at C, the frequency of the sound waves detected by the listener. Take a look at our equation. We had FL being equals to V divided by V plus Vs multiplied by the frequency of the source. Okay, as you can clearly see, if the velocity of the source increases, we're gonna have a way greater denominator. And then if you increase the denominator, the number as a whole is decreasing. So the frequency of the listener would decrease, right? So the answer to C is decreases. Yeah, we can clearly see that from our equation. And then 6.2.1, the spectrum of a distant star when viewed from the Earth is redshifted. Is the star moving away or towards the Earth? And 6.2.2 says that use the Doppler effect to explain the answer to question 6.2.1. Right, I'm interested on how you answered this question. So 6.2.1, is it moving away or is it moving towards? Let me know in the comment. And what reason did you give? Why are you saying it is moving away? If you said it is moving towards, why are you saying that that is the case? Let me know in the comment section.
So the siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. So we have the frequency of a source being 680 Hz. And then a man is standing with a detector that records the wavelength of the sound emitted by the siren, as shown in the diagram below. And yeah, there you have it on the left hand side. And then it goes on to say the speed of sound in air is 340 meters per second. So we have our V being equals to 340 meters per second. And then 6.1 says calculate the wavelength of the detected sound. This is quite an easy one because we all know that the frequency is equals to the speed in the medium divided by the wavelength, right? We are given the frequency of the emitted sound, and it's said to be 680 hertz. And then the speed of sound in air is 340 meter per second, right? So we have 340 divided by what we're interested in, the wavelength. From here, we just cross multiply and we get our wavelength. So we're going to have wavelength is equals to 340 divided by 680 hertz. And then 340 divided by 680, that is 0.5 meters. So the wavelength of our detected sound is 0.5 meters. And then we have 6.2, which starts by statement. It says the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of the sound of the sound, which differs from the previous reading by 0.05 meters. Okay, so we have a change in wavelength which is equal to 0.05 meters. Okay, before we go any further, it is said that the ambulance is moving towards the man, right? So from here, we should know that the new wavelength of the detected sound will be equals to 0.5 minus 0.05, which is 0.45 meters. Up to so far, there's no question that is asking us to do this, but then it's just obvious because I'm reading the statement and I understand what it is saying. So I know that the new wavelength that is going to be detected is going to be 0.45 meters. And then 6.2 says state the Doppler effect. That's just a definition. I don't expect anybody to get that wrong. It says the change in frequency, pitch, or wavelength of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. This definition is just basically the formula, really. It's the change in frequency, pitch, or wavelength of the sound detected by a listener because the sound source and the listener have different velocity relative to the medium of sound propagation. And then we have 6.3. So 6.2, that's the definition. And then 6.3, it says, how will each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? And then we have 6.3.1. It says distance between the wave fronts. The distance between the wave fronts is directly proportional to the wavelength. And if you can see here, I've already shown you that the wavelength will go down when the sound source is moving towards the listener. So for 6.3.1, we'll have decreased, right? Because the options we have is increase, decreased, or no change. So we're going to have decreased because the wavelength will go down. So that means that the distance between the wave fronts decreased. And then we move forward to 6.3.2. And then how will the frequency of the detected waves change? Okay, the frequency is equals to the speed divided by the wavelength, right? So frequency is inversely proportional to wavelength. The wavelength went down, so the frequency goes up, right? So we're going to have increased. And then 6.4 says calculate the speed of the ambulance, right? So in Doppler effect, there's really 2-3 formulas you can use. You can have the frequency equals to the speed divided by the wavelength. And then another formula you can use is always frequency of listener equals to V plus or minus the velocity of the listener divided by V plus or minus V plus or minus the velocity of the source multiplied by the frequency emitted by the source, right? And then this question says the speed of the ambulance. This formula cannot help us with the speed of the ambulance, so this is the formula we're going to use, right? So now we have to identify all the information we have and then decide on how we can determine the speed of the ambulance. So the ambulance is the source, right? So we are interested in this Vs here. We are interested in this Vs. We have V because V is the speed of sound in air. And then frequency of source, we have determined it. Oh, no, we didn't determine it. It is given to us as 680 Hz. And then frequency of listener, we can determine it because we now have the wavelength when the ambulance is moving towards, right? Which we determined to be 0.45 meters. So we're going to have frequency of listener equals to 340 divided by 0.45 and then that will be in the units of hertz. So let's leave it like that. Let's not solve it any further. We're just gonna keep it like that. So now we have frequency of listener equals to this is the speed of sound in air, and then the sound the listener is stationary. So we're going to have plus or minus 0, right? And then divided by the speed of sound in air again, V, and then the source is moving towards. When the source is moving towards, we get a minus in the denominator. So we're going to get minus the velocity of the source multiplied by the frequency emitted by the source. If you don't know how this formula comes about and why I'm choosing minus on the denominator, then watch my introductory video that I'm gonna link on the top left corner. And then the frequency of listener, we say that is 340 divided by 0.45, and then V is 340, then plus or minus 0, we don't have to put anything there. So we have 340 again minus velocity of source multiplied by 680 Hertz. Now when you add this step, it's just a matter of how you want to solve it, the mathematics, right? It's you're almost done with the physics here. So the way I'm going to solve it, I'm going to divide both sides by 680, right? So I'm going to have 340 divided by 0.45, and then everything divided by 680, right? And then if I divide by 680 on the right hand side, that 680 is gonna get cancelled out. So now we're gonna have 340 divided by 340 minus velocity of source. I'll go ahead and cross multiply. I'll get 340 divided by 0.45 multiplied by 340, right? And then minus 340 divided by 0.45 multiplied by velocity of source, which is equals to 680 multiplied by 340. So I can take this expression here to the right hand side. I'm gonna get minus 340 divided by 0.45 multiplied by velocity of source equals to 680 multiplied by 340 minus our expression, right? So let me just try copy it and paste, right? So minus this expression here, right? So after that, I'm gonna divide both sides by minus 340 divided by 0.45, right? So that I can isolate Vs. So I'm gonna get Vs equals to, let me copy this expression here. So I'm gonna copy that expression and then I'm gonna duplicate it. So now I have Vs equals to this expression divided by minus 340 divided by 0.45. And now I can put this entire expression here in the calculator and determine Vs. The reason why I don't want to press the calculator before I get to the answer is because I'm avoiding making mistakes, right? I rather put things in the calculator once and get the answer rather than put things in the calculator a lot of times and risk making a mistake, right? So I'm putting it on my calculator right now. So divided by minus 340 divided by 0.45, and that is exactly 34. Oh, 34. Why am I writing 340? Exactly 34 meters per second. If you have divided along the way, you've multiplied and you put it in the calculator, you're probably gonna get 33, something or 34, something. But then if you just solve it without putting it in the calculator and you only press the calculator at the end, you're most likely to get the most accurate answer. So I have a question here that I was doing with my learners during the day, and I just thought I should share it with you guys. So we have a sound source that is moving in an easterly direction towards the stationary learner at 15 meters per second. The frequency observed by the learner is F1. So when this sound source, right? Let me just write that down. So we have sound source. When it's moving towards the east, it's moving with a velocity of 15 meters per second towards the learner, right? The listener. And the frequency observed by the listener, it is said to be F1. And then it goes on to say when the source is stationary and the learner moves in a westerly direction. So now we have a learner moving towards the west. And then the learner is moving towards the source at 25 meters per second, right? So we have velocity of observer being 25 meters per second. The frequency observed by the learner is F2. So we have frequency observed, which is F2. It goes on to say that F2 is greater than F1 by 37 Hertz, right? So we're going to get F2 equals to F1 plus 37 Hertz. And then 6.1 says, write down the name of the phenomenon that the learner observes and state this phenomenon in words. So we know that the phenomenon is Doppler effect, right? Because the observed frequency and the emitted frequency are different because of the relative movement between the sound source, the listener, and the speed of sound in air. And then 6.2 says, assuming that the speed of the sound in air is 340 meters per second, calculate the frequency of the source. So let's start with our scenario 1, right? This is our scenario 1, where the sound source is moving towards the listener
with a velocity of 15 meters per second. So we know fully well that frequency observed is equals to the frequency emitted multiplied by v plus or minus the velocity of the listener divided by v plus or minus the velocity of the source, right? And then the frequency observed by the listener when the sound source is moving towards the listener, we are told that is f1, right? So we're going to substitute f1. And then this is equals to fs because we don't know what the emitted frequency is, right? And then the speed of sound in air is 340. And then it is said that the listener is stationary when the sound source is moving towards the listener, right? So we're going to have plus or minus 0 here. And then divided by 340 minus Vs, which is 15, right? Because the sound source is moving towards the listener. This is going to give us F1 equals to Fs multiplied by 340 divided by 325, right? And then we can name this our equation 1. And then now let's come to our second scenario when the learner is moving towards the sound source, right? So again, we are going to have FL equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs. And then what is FL? We are told that when the learner is moving towards the sound source, FL equals to F2, right? And then F2 is F1 plus 37. So we're going to have F1 plus 37 equals to Fs, which is unknown, right? And then we know fully well that our V is 340 plus or minus the velocity of the listener. So what is the velocity of the listener? The velocity of the listener, it is said to be 25 meters per second, right? So we're going to have plus 25 meters per second divided by 340 minus or plus 0, right? Because the sound source is now stationary. So this will be equals to F1 plus 37 equals to Fs multiplied by 365 divided by 340, right? We can go ahead and make F1 the subject of the formula. We're going to get F1 is equals to Fs multiplied by 365 divided by 340 minus 37, and then we can call this equation 2. So I want you to realize something. If we say equation 2 equals to equation 1, then we can solve for Fs, right? Which is what we want. And then equation 2 is equals to equation 1 because they're all giving us F1, right? So equation 2 is Fs multiplied by 365. This is 365. Divided by 340 minus 37, and it's supposed to be equals to equation 1. Equation 1, which is Fs multiplied by 340 divided by 325. So what we are going to do, we are going to make Fs the subject of the formula, right? So we're gonna have minus 37 equals to Fs multiplied by 340 divided by 325 minus Fs multiplied by 365 divided by 340. So if we take Fs as the common factor in the right hand side, we're gonna get minus 37 is equals to Fs multiplied by 340 divided by 325 minus 365 divided by 340. And then from here we can divide both sides by this expression, right? And we get Fs. So we're gonna get Fs is equals to minus 37 divided by the expression, which is 340 divided by 325 minus 365 divided by 340. And then if you put this in your calculator, you are supposed to get the value of Fs. And when I punch that in my calculator, I'm getting 1351.57 hertz. So if you can look at this problem that we just did, the physics is really straightforward, right? We have a scenario when the sound source is the one moving, and the scenario where the listener is now moving. As soon as you set up your equations, now you're just left with solving the math. So let's do 6.3. 6.3 says calculate the wavelength of the sound observed by the stationary learner, right? So we know that frequency equals to speed divided by wavelength. If we make the wavelength the subject of the formula because it's what we want, right? We're gonna get wavelength equals to the speed divided by the frequency. And then what is the speed? Because we're talking about sound here in air, right? We are told that the speed is 340. And then what is the frequency? The frequency is what we just calculated, right? Which is 1351.57, which is equals to 0.252 meters. And then 6.4. And then 6.4 says write down one application of the phenomenon referred to in question 6.1 in the medical field. So that's the Doppler effect, right? And one of the applications is ultrasound. And then another application is measuring the heartbeat. So you can write measuring the heartbeat, right? But this is the stuff you can just Google and you find it. And then 6.5 says the spectral lines from a star are shifted towards the longer wavelength of the spectrum. Does this represent redshift or blueshift? So longer wavelength, that is redshift. If it's shorter wavelength, then that is blueshift. A learner in a car moving at a constant speed of 10 meters per second. So we have V equals to 10 meters per second along a straight horizontal road. Records the frequency of sound emitted by a distant stationary source. So the source in this instance is stationary and the listener is the one in motion, right? The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. So we have our V new of 20 meters per second. So to say, the graph below, not drawn to scale, is obtained from the results. On the y-axis, you can see we have the recorded frequency, and then on the x-axis, we have the speed of the car. So let me sketch what is going on. So this question is saying that this sound source is stationary. What is moving away is the listener, right? On the first scenario, the listener is moving away at a velocity of 10 meters per second. And then on the second scenario, the sound source still stationary, but the listener is now moving away at a speed of 20 meters per second. The first question says, state the Doppler effect. This is the apparent change in observed frequency as a result of the relative motion between a sound source and an observer. 6.2 says use the graph to answer the following question. And then 6.2, there we have it. 6.2.1, write down the frequency of the sound source emitted by the stationary source. So the equation we have for Doppler effect is that the frequency observed by the listener equals to V plus or minus VL divided by V plus or minus Vs multiplied by frequency emitted by source. So for us to find the frequency emitted by the sound source using this equation, we need the frequency observed by the listener to be equal to the frequency emitted by the sound source. For us to obtain that using this equation, we need a VL here, the velocity of the listener, to be equals to the velocity of the sound source, so that V and V can cancel out, and then at the end we have FL equals to FS. As far as we know, the velocity of the sound source is 0, right? Because it's stationary. So we go to a graph and look at a point where the velocity of the listener or the car is 0, so that the frequency of the listener can be equal to the frequency of the sound source. And then if you look at the graph, there's a green point there I'm making. That is where we have 0 and the x-axis. And then on the y-axis, we have the frequency, which is equals to 700 hertz, right? So the frequency emitted by the stationary source in this situation is 700 hertz. Then the question is, and then it goes on to say, give a reason for your answer. The reason of the answer is that there's no relative motion between source and listener. They all have a velocity. So velocity of listener equals to velocity of source equals to 0 meters per second. No relative motion between the two. So the Doppler effect cannot take place, or its effect is 0 in this instance. Let's move on to the next question. 6.2.2. In which direction is the car moving relative to the source? Choose from towards or away. Give a reason for the answer. Again, we have to stick to the graph we have. That's what the question requires of us. So if when the velocity is 0, the frequency observed is 700 hertz. When the velocity is 10 meters per second, the frequency observed is 779.1. So it seems like when the speed of the car is increasing, the frequency observed is going down. That only happens when a vehicle is moving away, right? Whether the sound source is moving away from the listener or the listener is moving away from the sound source. But then in this situation, we know very well that the sound source is stationary. So the listener is the one moving away. So here we'll write away. And then the reason for that is that the frequency observed is less than the frequency emitted, right? Yes. Let's move ahead. 6.2.3 it says calculate the speed of sound in air. Okay, so what we're going to do, we have the data for when the speed of the vehicle is 10 meters per second and when the speed of the vehicle is 20 meters per second. So we're going to pick one between the two, and then we're gonna use it to find the speed of the air. So again, the first thing to do is to jot down the given information, right? So now we know that the frequency of the source is 700 hertz. So we're gonna write that down. The velocity of air is our unknown, right? And the velocity of the source is 0. So the velocity of the listener, now we have to pick one point between the two. It's either we start with 10 or we start with 20. So let's pick 10.
So there we have it, 10 meters per second. So on our Doppler effect, we're going to have one missing variable, which is the speed of sound in air, and then from that is just solving the math. So let's go ahead and do that. We have FL equals to V plus or minus VL divided by V plus or minus VS multiplied by the frequency of source, right? The frequency observed by the listener when the speed of the car is 10 meters per second is 679.1, which is equals to this V is what we are interested in, the speed of sound in air, and then the velocity of the listener, because the listener is moving away, we're supposed to have a minus on the numerator, right? If it was moving towards, then we're going to have a plus. So there we're going to have V minus 10 divided by the velocity of sound in air, and then the listener stationary, so we're going to have plus or minus 0 multiplied by frequency of source. Frequency of source is 700 Hz, so we're just going to have that there. So if we write this nicely, we get 679.1 equals to V minus 10 divided by V multiplied by 700. If I divide both sides by 700, I will get 679.1 divided by 700 equals to V minus 10 divided by V. Cross multiply, I get 679.1 V equals to 700 V minus 700 multiplied by 10. Take this value here to the left hand side. I get 679.1 V minus 700 V equals to minus 7,000, right? Yeah, there we have it. So now I can take V as a common factor. That will give me 679.1 minus 700 equals to minus 7,000. And then V is thus equals to minus 7,000 divided by 679.1 minus 700. Let me put that in my calculator real quick. It's taking a bit longer than I expected. Just give me a sec. So we have minus 7,000 divided by 679.1 minus 700. That is 334.993 meters per second. So yeah, that is what I'm getting. So what I'll ask you guys to do is to use the other point when the velocity is 20 meters per second and see if you get the same thing. This is a series of videos. I've done question 5, 4, 3, 2 from this question paper. So if you click on the channel, you'll get all of that. Please leave a like, subscribe, and I'll see you next time. In this video, we're going to do 18 past exam questions based on Doppler effect. So if you look at the left hand side, we already have a question there. Question 7. So let's go ahead and start. The first thing I like to do, I like to read the problem statement and I jot down all the information that I think would come in handy that will help me solve the problem. So let's go ahead and do that. Dolphins use ultrasound to scan their environment. Interesting. When a dolphin is 100 meters from a rock, it emits sound waves of frequency 250 kilohertz, 250,000 hertz, while it's swimming at 20 meters per second towards the rock. Assume that the speed of sound in water is 1,500 meters per second. The first question says, calculate the frequency of the sound waves detected by a detector on the rock. So in this instance, the rock is the observer, is the listener, so to say. So the dolphin is 100 meters from a rock. That's not important in solving this problem we have here. And then frequency emitted by the source is 250 kilohertz, which is 250,000 hertz, right? Kilo, it's 1,000. While it's swimming at 20 meters per second, so we know that the velocity of the source is 20 meters per second towards the rock. So let's just put an arrow there to denote that is moving towards. Then V of sound on water is 1,500 meters per second. Then we're supposed to calculate the frequency of the sound source, the frequency of the sound waves detected by the detector on the rock. So we have F of listener is equals to F of source, V plus or minus V of listener divided by V plus or minus V of source. So we are interested in finding VL. We have everything else. So in this case, it's just a matter of subbing in what we have in the equation. So we're going to have frequency of source is 250,000 kilohertz multiplied by 1,500, the speed of sound in water. And then the listener is stationary, so you can have plus or minus 0, it wouldn't matter. And then on the denominator we have 1,500 for the speed of sound in water. And then the dolphin is moving toward. If it's moving towards, then we have minus on the denominator. If it was moving away, then we're going to have plus. So we're going to have 1,500 minus 20, which equals to, now it's just a matter of putting that into your calculator. 250,000 multiplied by 1,500 divided by 1,480, and then that's going to give us 253,378,3784 hertz, which you can convert to kilohertz, and then you're going to have 253,38 kilohertz. That's it for this question. Maybe one thing that will have thrown you off is the speed of sound in water. That is 1,500. Maybe you are used to the speed of sound in air, and then you sub in 340 or 343, something around that, and then you're completely wrong. Okay, let's move ahead. 7.2 says, when the dolphin is 50 meters from the rock, another ultrasound wave of 250 kilohertz is emitted. How will the frequency of the detected sound waves compare with the answer calculated in question 7.1? Write down only higher, lower, or remains the same. Explain your answer. The frequency detected. So what's the formula of the frequency detected? It's F of FL equals to Fs V plus or minus VL divided by V plus or minus Vs. What are the variables that affect the frequency detected? Is the frequency emitted, the velocity of the sound in that medium, the velocity of the listener, and the velocity of the sound source. The distance between the two has no effect as far as this formula is concerned. So now, because the distance between is no longer 100 meters and it's 50 meters, it won't matter. So the right answer is remains the same, right? Remains the same. And then it says explain your answer. You'd explain your answer by writing this formula and stating that the distance between the sound source and the observer is not a variable, in the equation we use to determine the frequency detected. Let's go ahead and move to the second question. The first step again, read the statement that is given and write down any information that we feel would come in handy. So the siren of a police car produces a sound of frequency. So frequency of source 420 Hz. A man sitting next to the road notices that the pitch of the sound changes as the car moves towards and then moves away from him. 7.1. Write out the name of the above phenomenon. We know this is Doppler effect because the frequency is changing because of relative movement between the sound source and the observer. 7.2. Assume that the speed of sound in air, so we have V equals to 340 meters per second. Calculate the frequency of the sound source of the sound of the siren observed by the man when the car is moving towards him. So V of source equals to 16 meters per second towards him. We just denote that by an arrow. So back again, we're going back to the formula. F of L equals to F of S, V plus or minus VL divided by V plus or minus Vs. So what would you do? So maybe the right thing to do right now is pause the video and try it out by yourself and see if you will get the answer right. I'm assuming you paused the video and you tried it by yourself, and then now we can do it together. We're interested in finding the frequency observed. So that is FL. Frequency of source, we already wrote it down when we were reading our problem statement. That is 420 Hz multiplied by the speed of sound in air, which is given as 340 plus or minus 0. The observer is stationary. 340. Because it is moving towards, again, on the denominator, we have a minus. If it was moving away, then we'd have a plus. So that is minus 16. As the speed of the sound source is given, equals to, now it's just a matter of putting it into the calculator. We have 420 multiplied by 340 plus or minus 0, so we don't have to put anything there. Then we have 340 minus 16, which is going to be 440.74 Hertz. Yeah, that is it. 7.3.1. The question says, the police car moves away from the man at constant velocity, then slows down and finally comes to a rest. How will the observed frequency compare with the original frequency of the siren when the police car moves away from the man at constant velocity? When it's moving away, the observed frequency is gonna be smaller than the original frequency, because we're going to, in the denominator, we're going to have a minus sign, and then on the denominator we're going to have a positive sign. So if you increase the denominator and then you keep the numerator the same, the number overall is going to be smaller. There's no need for an explanation. 7.3.2. So let's go back to the formula. We have F of L equals to F of S, V plus or minus VL. Everything we say in every calculation we do, we're basing it in this formula and nothing else. So they're saying that the car is slowing down. So this Vs is getting smaller, right? So if Vs is getting smaller and then the numerator is the same, then FL will go up, because now we're dividing by smaller number. So the observed frequency will increase. It sounds very counterintuitive because the car is still moving away, but then if we base it on this formula, then it's supposed to increase. Let's move ahead. Another question 7. An ambulance with its siren on moves away at constant velocity from a person standing next to the road. The person measures a frequency which is 90% of the frequency of the sound emitted by the siren on the ambulance. Name the phenomenon observed. We already know this Doppler effect because the frequencies observed is different from the frequency emitted due to relative movement between the sound source and the observer. 7.2. If the speed of sound in air is 340 meters per second, calculate the speed of the ambulance. So one thing that can throw you off in this situation is the fact that we're not given the frequencies per se. We're given that now the observed is 90% of the emitted. So because the observed is less than the emitted, then we know the vehicle is moving away, right? So we have FL equals to FS V plus or minus VL divided by V plus or minus VS. FL, that which is observed, is equals to 90 FS, right? And then FS is just FS, it's itself 90% FS, not 90 FS. And then V is just the speed of sound in, I'm very sorry for that. V is just the speed of sound in air, and then VL is 0, the observer is stationary, and then VS is our unknown. So let's go ahead and put that into the equation. So FL is 90% of FS, right? So that's just 0.9 FS, which equals to FS itself. Then we have multiplied by 340. The observer is stationary, plus or minus 0. 340 again, and then it's moving away. So if it's moving away, we're supposed to have plus on the denominator. If it was moving towards, then we're going to have minus on the denominator. So plus VS. What I'm going to do, I'm going to divide both sides by FS, right? So if you divide, so if you divide the right hand side by FS, FS and FS are going to cancel out, and then on the left hand side, if you divide 0.9 FS by FS, you're just going to be left with 0.9. So we have 0.9 equals to 340 divided by 340 plus VS. So now let's cross multiply. We have 0.9 multiplied by 340 plus 0.9 VS equals to 340 multiplied by 1. Let's take this, what we have here, to the right hand side. So we're gonna have 0.9 VS equals to 340 divided by 0.9 multiplied by 340. Now we divide both sides by 0.9, so we're going to have VS equals to 340 divided by 0.9 multiplied by 340 divided by 0.9 equals to now it's just a matter of putting that in the calculator. Let me go ahead and do that. So we have 340 divided by 0.9 multiplied by 340 divided by 0.9. 40 divided by 0.9 multiplied by 340. So VS is 1.2345 meters per second. This answer seems very fishy. It's so small. I don't know if I did something wrong, but yeah, let me just move on. Question 6. We're going to read the problem statement again, like we always do. The siren of a burglar alarm system has a frequency of So frequency of source, I'm assuming frequency of source equals to 960 Hertz. During a patrol, a security officer traveling in his car hears the siren of the alarm of a house and approaches the house at a constant velocity. A detector in his car registers the frequency of the sound as 1000 Hz. So frequency observed is 1000 Hz. Name the phenomenon, blah 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 blah. We know that that's the Doppler effect because the frequency is changing due to a relative what? It's changing due to relative movement between the sound source and the observer. 6.2. Calculate the speed at which the patrol car approaches the house. Use the speed of sound in S. Back to the basics. FL equals to FS V plus or minus VL divided by V plus or minus VS. FL is 1000. We're given that. FS is 960 Hz. We're given that. And then V is 340. Says we're supposed to calculate the speed at which the car is approaching. So now is the velocity of the observer that we're supposed to calculate. If it's approaching, then on the numerator we have a plus, right? Plus VL. If it was moving away, then we'd have minus. Yeah. On the denominator we have 340. The sound source is stationary, so plus or minus 0 doesn't matter. So that is 1000 equals to 960 multiplied by 340 plus VL divided by 340. I'm gonna divide both sides by 960, so we're going to have 1000 divided by 960 equals to 340 plus VL divided by 340. We're going to cross multiply, so we're going to have 340,000 equals to 960 multiplied by 340 plus 960 multiplied by VL. I'm going to take this which we have here to the left hand side so that I can isolate VL. So we're going to have 340,000 minus 960 multiplied by 340 equals to 960 VL. I'll divide both sides by VL, so we're gonna end up with VL equals to, let me put that into my calculator, 340,000 minus 960 multiplied by 340 multiplied by 340 divided by 960. So that is 14,1667 meters per second. Yeah, we stick to the basics again. We write down the information we have, we sub in, and then we solve for the variable. Let's move ahead. 6.3. If the patrol car had approached the house at a higher speed, how would the detected frequency have compared to the first observed frequency of 1000 Hz? Every question we have, we stick to the formula. So let's go ahead and do that. FL equals to FS V plus or minus VS VL, I meant, divided by V plus or minus VS. So we're saying the car is now approaching at a higher speed. So we're increasing this number here. So we're increasing the numerator and keeping the denominator the same. So if you increase the numerator and keep the denominator the same, then the overall number will be higher, right? So in this instance, the frequency will be higher than. To prove that, if you have 1 over 2, then this is 1 over 2. But then if you increase the denominator to 4, if you increase the numerator to 4, then let's say you have 4, and then you keep the denominator the same, then now you have 2, and then 2 is greater than 1 over 2. So every time you increase the numerator and you keep the denominator the same, the number overall will go up. Let's move ahead. Question 6. The whistle of a train emits sound waves of frequency 2000 Hz. So f of sound source 2000 Hz. A stationary listener measures the frequency of these emitted sound waves at frequency of listener 2080 Hz. So we can see that the frequency observed is greater than the frequency emitted. So it's either the sound source is moving towards the listener, or the listener is moving towards the sound source. Name the phenomenon responsible for the observed change in frequency. That's Doppler effect. The frequency observed is different from the frequency emitted because of the relative change in position between observer and listener. 6.2 is the train moving away from or towards. It's moving towards, right? It's moving towards because the observed sound is greater than the emitted. 6.3, calculate the speed of the train. F of L equals to F of S. Sticking to the basics again, the formula we use, VL divided by V plus or minus Vs. The observed frequency is 2080 Hz equals to 2000 Hz. Speed of sound in air 340. It says the speed of the train. Okay, so plus or minus 0 here. The listener is stationary. 340 minus Vs. It's minus in the denominator if the sound source is moving towards. If the sound source was moving away, then we were going to have plus on the denominator. So let's go ahead and do that. Divide both sides by 2000, right? So it's 2080 divided by 2000 equals to 340 divided by 340 minus Vs. We're going to cross multiply. So we're going to have 2000 multiplied by 340 equals to 2080 multiplied by 340 minus 2080 Vs. So I'm going to take this expression here to the left hand side so that I can isolate Vs. So we're going to have 2000 multiplied by 340 minus 2080 multiplied by 340 equals to minus 2080 multiplied by Vs. And then now I'm going to divide both sides by Vs and see what we get. So let me go ahead and put that into my calculator. So we're going to have Vs equals to okay, let's see what we have. 2000 multiplied by 340 minus 2080 multiplied by 340 divided by minus 2080. That gives me 13.0769 meter per second. I think that's around about it. Speed of the train. 6.4 says, which will the frequency observed by a passenger sitting on the train be greater than, equal than, or smaller than 2000 Hz? Explain the answer. Well, the frequency observed by a passenger. Oh, okay. The passenger is in the train. So if the passenger is in the train, okay, yeah. Interesting question. 6.4. Let's stick to the formula again, like we always do. FL equals to FS V plus or minus VL divided by V plus or minus VS. This Fs is remaining the same. V is the same. V is the same. So now, because we're talking about the passenger in the train, V passenger is the same as Vs. So basically what we have on the numerator is equals to what we have on the denominator. So this is just gonna cancel out, right? And then we're just gonna be left with FL equals to Fs. So the answer here would be equal to. Why are we saying equal to? We're not taking a guess. We're not just saying it because we have to choose one of the options. We're basing it on the formula. Each and every question you come across, you're going to be basing it in this formula. That's it for this question. Let's move to the next one. Question 6 again. A lot of question 6, it seems. A train approaches a station at a constant speed. So V of source, I'm assuming it's source, I can always change. With its whistle blowing at a frequency, okay, frequency of source 458 Hertz. Standing on the platform, he has a change in pitch as the train approaches him. Oh, okay, somebody approaches him, passes him, and moves away from him. Okay, 6.1. Name the phenomenon that explains the change in pitch had by the observer. Change in pitch had by the observer, that's Doppler effect. The pitch is changing because of relative movement between the observer and the sound source. 6.2. Calculate the frequency of the sound that the observer hears while the train is approaching him. Use the speed of sound in air as 340 Hz. Calculate the frequency. Okay. So we are looking for FL, which is equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs, like we always have. The emitted frequency is 458 Hz, right? Speed of sound in air we given as 340. The observer is stationary plus or minus 0 divided by speed of sound in air 340. The train approaches, so it's moving towards, then we subtract Vs, which is 20. If it was moving away, then we're going to add. Then that's it. We just plug that into the calculator. So let me go ahead and do that. 458 multiplied by 340 divided by 340 minus 20, 320. That is 486,625 Hertz. 6.3. How will the observed frequency change as the train passes and moves away? From the observer, write down all the increase. It's going to decrease. It's going to decrease. Why are we saying it's going to decrease? Let's go back to the formula. FL equals to Fs V plus or minus VL divided by V plus or minus Vs. Because when it's moving towards, on the denominator we have a subtraction of Vs, right? So if you keep the numerator the same and you decrease the denominator, the number goes up. So when it's approaching, FL goes up. When it's moving away, we have an addition on the denominator. So you keep in the numerator the same and you increase in the denominator. The overall number goes down. 6.4. How will the frequency observed by the train compare to that of the sound waves emitted by the whistle, by the train driver? The train driver and the whistle are traveling at the same speed, so we're going to have Vs equals to VL. If we put that into the equation, we get VL equals to Fs V let's say plus or minus VL divided by V plus or minus VL again, because VS is the same as VL. So in this case, the numerator and the denominator are going to cancel out and going to have FL equals to FS. So for 6.4, it will be equal to.
Let's move ahead and do questions that are a bit different from what we're doing, that involve graphs and so on. So on the left hand side, we have a question here, question 6. We're going to start by reading the problem statement like we always do. A bird flies directly towards a stationary bird watcher at constant velocity. The bird constantly emits sound waves at a frequency of 1650 Hz. So from that, we already know that the frequency emitted by the source is 1650 Hz. The bird watcher hears a change in pitch as the bird comes closer to him. So the bird is moving closer to the observer. And then 6.1 says, write down the property of sound that is related to pitch. By definition, Doppler effect is the change in frequency, wavelength, or pitch because of relative movement between an observer and a sound source. So a property that is related to pitch is frequency, right? But at the same time, frequency is related to wavelength. So we're going to write wavelength slash frequency like I just did. 6.2, give a reason why the bird watcher observes a change in pitch as the bird approaches him. This is because of the Doppler effect, right? When the bird watcher, when the bird is moving towards the bird watcher, the waves are compressed, so the wavelength goes down and the frequency goes up. So that's why there will be a change in pitch when the bird approaches the bird watcher. Let's go ahead. 6.3. We have a graph, a pressure versus distance in meters. The first question says, from the graph, write down the wavelength of the detected waves. Again, we go back to definitions. What's a wavelength? A wavelength is the distance between two crests, right? So if we have this crest here and then we have this crest here, this line joining the two is our wavelength. So if we have this line here cutting the axis and we have this line cutting the axis, the distance between these two is the wavelength. So you can see there from the graph that we have 0.3 minus 0.1, which will give us 0.2 meters. If we use the other point, if we use the crest instead, between 0.3 and 0.2, we have 0.25 minus between 0 and 0.1, we have 0.05, which will also give you 0.2 meters. So the wavelength, we calculated it by just sticking to the definition of what a wavelength is. 6.4.1, the first question says frequency of the waves detected by the bird watcher. So we know from definition that frequency is given by the speed of the certain wave in a certain medium divided by wavelength. We've already determined what the wavelength is. It's 0.2 meters. And then on the question, we're given that the speed of sound in air is 350 meters per second. So we're just going to plug that into the equation. We're going to have 340 meters per second divided by 0.2 meters. 0.2 meters. So let me go ahead and put that into the calculator. We're going to have 340 divided by 0.2, which is going to give us 1,700. The SI unit of frequency is Hertz, which makes sense. The emitted frequency is 1,650 Hertz, right? and the bird is moving towards the bird watcher. So we anticipating a frequency that is greater than that which is emitted, and then that is true because as you'd see, 1700 is greater than 1650 hertz. Moving to the next question, 6.4.2. It says magnitude of the velocity at which the bird flies. We have frequency, we have the speed of sound in air, we have the wavelength is. So the formula we're going to use the Doppler effect formula, right? Which is given by the frequency of the listener observes equals to the frequency of the source multiplied by the velocity plus or minus VL divided by V plus or minus VS. The frequency observed by the listener is 1700. We calculated in 6.4.1. So we're just going to go ahead and put that on. So that will give us 1700 equals to 1650, which is the frequency emitted by the sound source, right? V is 340 is given on the question. The listener is stationary, so we're going to have plus or minus 0. The sign won't matter in this case. And then 340 again, because the sound source is moving towards the observer. In the denominator, we're supposed to have minus. If it was moving away, then we're going to have plus. So we want to have minus V of sound source, which is our unknown. So what I'm going to do here, I'm going to divide both sides by 1650. So let me just go ahead and do that. So we're going to have 1700 divided by 1650 equals to, in the right hand side they're going to cancel out, so we're just going to be left with 340 plus or minus 0, which will just give us 340 divided by 340 minus Vs. Now what I'm going to do, I'm going to cross multiply. So I'm going to have 1700 multiplied by 340 minus 1700 multiplied by Vs, which is equals to 1650 multiplied by 340. I'm going to take this expression to the right hand side so that I can try and further isolate Vs. So I'm going to have 1700 Vs equals to 1650 multiplied by 340 divided by 1700. I'm moving a step forward. I'm still supposed to take that expression to the right hand side. So let me do that. It's going to be minus 1700 multiplied by 340. So after I've done that, I can then divide both sides by minus 1700, which is here. So let me just write that down for clarity. 1700 cancel out. So we're going to have Vs equals to 1650 multiplied by 340 minus 1700 multiplied by 340. Everything divided by minus 1700. So that's it for this question. I'm just going to plug that into the calculator. 1650 multiplied by 340 minus 1700 multiplied by 340. Everything divided by minus 1700, and that gives me 10 meters per second. It seems too good of an answer, but I can't notice anything I did wrong, so I'm assuming it's right. Let me scroll down and look for a question that has a graph in it so that we can do a question that's a bit different. Okay, we have a table there, so let's just do this question. So question 6.1, start by reading the problem statement like we always do. The data below was obtained during an investigation into the relationship between the different velocities of a moving sound source and the frequencies detected by a stationary listener. For each velocity, the effect of wind was ignored in this investigation. The first question says, write down the dependent variable for this investigation. Here on the problem statement, it says the relationship between different velocity and the frequencies detected. So we are differing the velocities and we figuring out what the detected frequency is. So the dependent variable is the frequencies, and then the independent is what we are switching around, which is the velocity, right? So dependent variable is the frequencies detected. If it was looking for independent variable, it will be the velocities of the sound source. 6.1.2 state the Doppler effect in words as the change in frequency, pitch, wavelength of a frequency observed by a listener because of relative movement between a sound source and the listener. 6.1.3 was the sound source moving towards or away from the listener? Give a reason for your answer. Okay, let's stick to the equation, right? FL equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs. If you look at the denominator here, we have Vs, right? Plus or minus Vs. If the sound source is moving away, we have a plus on the denominator. If you have a plus on the denominator, this whole number will go down. So the frequency observed will be going down. If it's moving towards, you will have a minus on the denominator. So the whole number will go up. So in our case, the frequency is going down. We start with 900, we have 8745, we have 850, we have 897. So it means we have a plus here on the denominator, and we only have a plus on the denominator when the sound source is moving away. So here we're going to have away from, because we're supposed to write towards or away from, and then give a reason for the answer. The reason is that the frequencies observed by the listener is decreasing, right? So it only makes sense that it is moving away. So 6.1.4 says use the information in the table to calculate the speed of sound during the investigation, right? I think the trick of the question here, I think, is to realize that for experiment 1, Fs equals to Fl, right? So to elaborate on that, we know that Fl equals to Fs V plus or minus Vl divided by V plus or minus Vs, right? In experiment 1, the velocity of the source is 0. The listener is stationary, so the velocity of the listener is equals to 0. If we put that into the equation, we're going to have Fl equals to Fs V plus or minus Vl divided by V plus or minus Vs. But Vs and Vl are 0, so we're going to end up with Fl equals to Fs multiplied by V plus or minus 0 divided by V plus or minus 0. This and this just cancel out, so Fl equals to Fs, right? So the frequency emitted by the sound source is basically 900 Hertz if you look at experiment 1 and pay attention to details. So to calculate the speed of sound during the investigation, we'll pick any of the other remaining experiments. So let's pick experiment 3 because it has like 20 and 850. 850 is better to work with compared to 874. So Fs, we deduce that is 900 Hertz, right? And then Fl for the third experiment is 850 Hertz. Vs is 20 meters per second. We're given that. And then we sub VL equals to 0. V is our unknown. So let's plug that into the equation. 850 equals to 900 multiplied by v plus or minus 0 divided by v minus 20 plus 20. I meant we plus in because the source is moving away. If the source was moving towards, then we're going to have a subtraction on the denominator. So let's divide both sides by 900. We're going to get 850 divided by 900 equals to v divided by v plus 20, right? Let's go ahead and multiply. We're going to get 850v plus 850 multiplied by 20, which will give us 900 multiplied by v. Let's take the 850v to the other side. We're going to get 850 multiplied by 20 equals to 900v minus 850v, which will just be 50v. So we're gonna get 850 multiplied by 20 equals to 50v. Divide both sides by 50. This would imply that v equals to 850 multiplied by 20 divided by 50. Let me plug that into my calculator. That will give us 340 meters per second, which is something you'd expect. You'd expect an answer around 340. Yeah, that's it for that question. Let's move ahead. 6.2. The spectral lines of a distant star are shifted towards the longer wavelengths of light. Is the star moving towards or away from the Earth? It's moving away from the Earth. It is shifted towards the longer wavelengths, then is shifted towards the red end of the spectrum. It's a redshift, and the redshift occurs when a star is moving away from the Earth.